Hello, everybody. So, got a couple things to go over tonight. Um, this week we're moving on to module 4, which is software, which means I will probably have the notes in my hand the whole time because that's the subject I teach most often, and I don't need to go down any deep rabbit holes. If you all ask questions, we can go down a deep rabbit hole. I don't need to get distracted and get into very high level details in this class. So I'll probably have the notes in hand all week so I don't drift off and talk about other stuff. I made a change to the module 4 discussion board, which again this week, it looks like a lot of people did not get posts on the discussion board. Remember, there's 2 due dates on the discussion boards. The first one is due by Saturday, and that way there's time to reply. As if you post to the discussion board now, there's not really much time to reply before midnight. So please get those in before earlier in the week instead of waiting until the last minute. The next one's a little bit different though. Let's look at the assignment that's on there. And the Wi-Fi is running really, really slow. So my PC might end up a second or two behind what I'm talking about, but maybe that'll pick up in a few moments. Nope, still looks like it's going really, really slow. So the next discussion board is a little bit different as far as how you'll write it. There's a discussion board topic, like always, but the main point of the discussion board this week isn't necessarily the topic that you're discussing. So this week, there's a requirement that you need to have a chatbot write the discussion board for you. And then you're going to evaluate, and in the reply section, discuss with your classmates about how that went. Those things have been coming up, they've been popping up like weeds all over the place. What reminded me this is a new one came out this morning that seems to be very, very promising. That reminded me that I was intending to talk about chatbots or require you to use one. And when I tried it, the first time I tried it, all the classes did something different, and it seemed to work best in discussion boards. You can get your initial post from the discussion board and then reply to your own post talking about how it went for you. And then the replies to your classmates, that's a good topic for discussion. That's how those go. So I just copied a topic over from a different course. It's one about databases. It's this one. So there's a topic there but basically you'll feed that topic into a chatbot. And I did ask that everybody use ChatGPT for it. That way everybody's using the same thing. There are lots and lots of alternatives and new ones coming out all the time, which is what reminded me to do that this morning, that there was a new one that came out that looked like it would be really, really promising for schoolwork. The reason I want to do that is to cover a few things about using chatbots, which fits with our topic this week, which is software. This is a piece of software. It handles a lot of work for us. I've been promoting things like that for years about writing code. Text files were necessary in the 1940s and 50s. It seems consistent year after year after year. Students really, really like writing the text files, writing the programs in text files. Software development industry at large has moved on from that. It may heading towards game development in particular. So you will probably it'll accept the programming languages, but there's graphical scripting things, visual scripting things, which are the standard for the industry because they're designed to match what graphic artists are trained with. It's node-based scripting. Might try to take a look at it at some point, but instead of writing the text file, you drag your mouse around, drag pictures around, and connect the little picture drag and drop to connect the pictures together and put your code together that way. Has really nice advantages that it links to what's running. So then when the program's running, instead of just a text file, the arbitrary keywords that turn into something different entirely before they run, with the graphical ones, that can link back the other way. So when the program's running, you can see the data flowing through there. Makes it a lot easier to debug, but that's the standard for game development instead of writing the text files, which are very, very lengthy and very, very prone to typos. And they use keywords that most people haven't heard. Like some of the most important keywords in game development don't show up until at least a 400 level math class. Quaternions, some people see it in a 400 level math class. Some people don't see it until they get to graduate studies, graduate level mathematics. So some of the keywords throw people off too and stuff, but humans make typos. Everybody's aware of that, right? Anybody made a typo at least this week? And we're only on Tuesday. I'm sure everybody's, yeah, I see heads nodding. We're only on Tuesday and everybody in the room nods their head. Yeah, I've made at least one typo this week. Humans do that. Machines never make typos. So there's things like that. And that's really what a chatbot is. So part of the reason I included this is to, so I could talk about it and show you all how to get the optimization out of it. So I did request that everybody use ChatGPT for that. So let's just use that here. That way we're all using the same thing, because before the semester, I didn't anticipate how quickly those were going to show up. We're getting 2 or 3 new ones every week. And that's just the ones that are being promoted and marketed. There are thousands and thousands of those that nobody mentions on a large scale, like showing commercials for them, like we see with ChatGPT, or the equivalent of commercials. Because some things are hard to advertise. Software is a great example. Our topic this week, we're going to talk about software. Just mentioned the text files, the traditional way of writing code. Still a very common one, but as far as the field at large, it's disappearing in the field at large, especially now that chatbots can handle the actual typing part. AI, so there's an intelligence is sort of implied there, but they're not intelligent. So like chatbots, what they can do is they can identify when one sentence is better than another. So we give them a topic and they generate thousands of sentences and then pick the best one. That's why it looks so good. But at the same time, there's some drawbacks to that. The very first thing is do not trust these things. They have no qualms about lying to you, and they will put it in a really, really nice looking sentence. You will ask them for sources, and they will give you something that is exactly formatted the way a citation should be formatted. But the thing is, they'll make up the article and make up the author, and they'll make up all the stuff in it. So do not trust these things. Most of them were trained on social media. So basically they will cite Facebook for information and then tell you it came from a scholarly article. They will also just make up information because that randomly generated sentence looks better than the one that has accurate information. It ranks higher. So what chatbots really do is they can evaluate sentences, put together good looking sentences. And I have the internet connection is really slow tonight, so hopefully it'll open up here and we can take a look. Okay, there. Should recognize it.
Also, ChatGPT is just slow in general since so many people use the website.
Yes, it's highly marketed. Oh yeah, I started talking about marketing. With software, there's not really commercials for text editors like we would use for software, right? So Microsoft wanted to promote their text editor, their latest one's VS Code. So to replace commercials, anytime somebody that works at Microsoft has downtime, they're supposed to make a YouTube tutorial, and throughout that tutorial, talk about how great VS Code is for doing that thing. The result of that is we get tons and tons and tons of tutorials on IT subjects from some of the best programmers or really high tier software or IT people, because Microsoft has more than just the software. That's their main thing. But really, it's a promotional thing, and they just keep talking about that text editor, which there's really nothing special about that text editor. I actually don't use it myself. There's the things that are special about it make me not use it at all. If you have it installed on your computer, don't uninstall it. If you have VS Code, don't uninstall VS Code.
Bye.
It makes changes. And
Glad it's
when you uninstall it, it doesn't make the changes back. So for example, if you have VS Code on your computer, how did I sign into this before? Surely I signed in with Google. If you have VS Code, it will make some changes so that if you uninstall it, you can't run Python afterwards. It makes changes in the registry. And it doesn't undo them when you uninstall it.
I installed it on this laptop in process, and it just didn't bother to uninstall it.
Yeah, so don't uninstall it. It's Microsoft. That's a different issue. Shouldn't get into that. So if you ever install VS Code, don't uninstall it. Things will stop working very problematically, which I don't know why they did it. A strange thing. But there's not a lot of ways to promote these. That's why I like when ChatGPT first showed up, it showed up in like tons of things that look like news articles talking about people using it to cheat. Those weren't articles. Those weren't real articles. And that probably happened before anybody ever tried to use it that way. But I consider it more of an alternative keyboard. Instead of typing one letter at a time, it types the entire sentence at a time. And there's different ways we can use it. So one of them goes back to the goal of what it was created for. I must have used a different email the first time I signed in because I thought there would be some stuff saved there. In general, the AI that we've started using, so like Siri, Google Assistant, all of that stuff, basically what we do with that is just bark orders, right? Just open it up, like, or we tell Alexa to do something, and it is just directly giving it orders over and over and over again. And that's generally not the best way to interact with things, right? I have a bunch of cousins that teach like elementary school and stuff, and they said it's starting to be a problem around people that are 5 to 6 years old because that's how they learn to communicate to other things, the way we bark orders at Alexa. So they just, there's all the stuff that I did before. So they just bark orders at everybody. They show up at kindergarten and first grade, and that's the only way they know how to interact with others is those demands like we would give to Siri or Alexa and all that. So a bit problematic, but in general, not the best way to interact with things. Anybody ever seen old episodes of the Jetsons? Rosie the Robot? They wanted, and I say lots of people wanted something more like Rosie. There's some time sensitive things there that wouldn't show up today, but that general interaction, not the racist undertones with Rosie the Robot, but the way they interacted with Rosie the Robot, it was just a machine that they would have a normal conversation with. The thing that often shows up in Hollywood. That's what the goal of these sort of chatbots was for. These are not big, massive software projects that take forever. That last Facebook project that they hired 43,000 programmers for. At the end of it, the next project they needed 32,000 programmers. So the standard way to report that is that 11,000 programmers were laid off, but they successfully finished the project and they only needed 32,000 for the next project. Big, huge things in that project, that next project, those 32,000 programmers are going to work for a year and a half on that project. Big, huge piece of software. Chatbots are not like that. Chatbots are a reasonable homework assignment. So I could do it in about 20 minutes. I've done it a couple times. For your first time people are seeing that in the software development class, I usually double the amount of time it would take me. So say 45 minutes, which makes it a very reasonable homework assignment. So it's not a big, huge, complicated thing to create these. It's probably a big, huge, complicated thing to invent them. But now they've been invented, we're not making them from scratch every time. We just have to put the pieces together in a new combination. So it goes really, really quick. And what we're going to do, there's a couple ways to interact with it. The one you probably hear about is putting a prompt in there, right? I've asked for a couple, so like history of the Java programming language. That's something we might see in an assignment, right? Give a history of that. Whoops, the typos. Programming language. And when we run that, it'll start spitting out things. They added some stuff, make it look like it's typing slowly. It probably already has 10,000 versions of this. It's some of the most powerful servers on earth right now. So it does not take it that long to type a couple of words. That's just an animation to add in later to get to the chat thing. But we put in that prompt and it starts spitting out an essay, no problem. That's what a lot of people think of, but that's not the best way to use one of these things. They were designed for the conversational aspect. So what you really want to do is guide the conversation with them. So instead of just putting in the whole prompt, you'd want to ask smaller questions like, how did the Java programming language come about? And get the little sections. So basically for an essay, instead of just putting in that whole prompt, you still want to put together your thesis and an outline and all of that stuff, and then guide the conversation to follow that outline. Keep tying things back to your thesis. Kind of like you're talking to your friends and they want to switch the topic, right? Maybe it's a sensitive subject that they don't want to talk about for some reason, needs discussed. So you just have to keep bringing it back to that. That's how you want to interact with the chatbot. Keep guiding it on there. And then you get like a sentence or a paragraph, but it's going to be much more detailed and in the order you put it in. So a human still has to do the thinking part. It can write, and the same thing for code. Like it can write code, but if we just ask for a big, large program all at once, it would get lost on what to do. So if you need it to write code, you need to be kind of specific. So like here in the prompt, my Wi-Fi is messing up again. So as soon as my laptop reconnects to the Zoom call, I was going to type some code in the prompt and show how to do that because we're on software this week. So that's another use for chatbots. Chatbots are better at typing code than we are. However, they cannot create an algorithm. There's an I in there, the AI, but it's not really intelligence. And yeah, I completely lost connection, so I have to wait for, I don't know why the internet's so bad. Let me try a different one. Are there different connections?
I've used it to make Linux scripts. It's like I know how to do this in one language, but I can't convert it to like Mint or Ubuntu or all that. So I just have like, hey, how do you do this and that? And it just tells me.
Yes, exactly.
It's so useful.
Okay, I have no idea why the Wi-Fi is down here. Maybe if the guest Wi-Fi works better.
Student Wi-Fi is working perfect. If you want to hop on that.
Student Wi-Fi, the guest Wi-Fi can be the slowest sometimes, but at times the guest Wi-Fi will be quicker because there'll be lots of students on the student Wi-Fi and nobody will be on the guest Wi-Fi. So something like this, when everybody on campus is probably in class right now, I tend to go to the guest Wi-Fi first. If there was a big event, that would be different. Oh, reload this. Okay, so we get back in here and in the prompt, we could put in something specific. Like if we wanted C++ code, can you make a person object in C++? and it should just spit out a bunch of code. Yeah. So it gave us that. It tried to guess at some parameters. So it took a good first guess, writes all the code for us, and then we're ready to copy and paste it. And then went ahead and did the instantiating. So just like the sentences, it can put a really good sentence together, but it can't put an algorithm together and figure out how to use that. You can see the examples. All it did with them is print the stuff out. Actually, it didn't print them out. It skipped a step there. It called the thing that would print it to the screen if we asked it to print it to the screen, but it didn't do anything with the return result of that. So there's still little gaps in there. So you want to be specific, and well, just like I mentioned with the essay, you want to you're the intelligent one, so you still want to put the thesis and the outline together of how that essay is going to go. Same thing with code. You want to put your algorithm together. Algorithm is the steps you need to walk through to accomplish a task. An intelligent creature still has to do that, but the machine's better at typing the actual text code, which is still a remnant, because obviously it's a machine. It could type the machine language code. Well, maybe not machine language, at least assembly language or byte code, something the machine would understand. Machine language itself is particular to the machine we're on. So like my laptop runs a different machine language than your laptop. It has to be unique for that particular machine, but there's some other levels in between that high level one that makes sense to humans and the actual machine code that are cross-platform compatible or cross-machine compatible and all that. But if you want to write code, make sure you ask for the code specifically. I've seen a lot of people do that. They'll ask for like one line of code, just little bitty pieces. But you can ask for big chunks. And the reason I require that is to get started working with it. Try different things. So for that discussion board this week, take that topic and maybe try putting in the topic all at once and see what it spits out for the whole post. And then come back and try guiding a conversation to what you think that response should be, and see how your results go. It's a tool that's not going away. If you're heading into IT, you're going to need to know how to use it. If you're heading into software development, creating a chatbot is like easily a homework assignment size thing. They're not big, massive projects. Inventing them was big and massive. That took some of the smartest people in the world years and years and years to do. But now that they're invented, we can just put the pieces together in different orders to make new ones. And that's easily a homework assignment. And then you get custom ones, right? So if you want to make, you customize it to your needs. ChatGPT and Bard and a few others, those are generalized to fit any purpose. But a tool built for a specific purpose is almost always going to be better than using a general purpose tool, right? Like pliers are used for grabbing things. So you could use pliers to take out a screw, but a screwdriver would be way, way better to take out a screw. Because the general tool can grab it and turn it, but it's definitely not the best way to remove a screw. The tool specifically for that would be better. So custom chatbots, if you're heading in software development, is something you're probably going to make a lot of, depending on the business needs. And it's easily a homework assignment, so you will see it before long. They're not difficult to put together. Once you have all the pieces, y'all have probably seen that. All of IT is really like that. So that's a nice segue back. So give that a try. Try a couple different things, and then discuss as you post replies to each other. The discussion part is about how that went for you. Things that you found worked well, or what didn't work well, or if somebody else seemed to have better results than you did, that's what they did.
So is the topic just distributed databases?
Yes.
So then we just fit that in a sentence and ask it like.
Yep. Ask it what it is, transparency features. It'll spit something out, and then this one. Well, there's two on there. When when would it be advantageous to have a distributed version versus a centralized version? Because there are pros and cons to both, obviously. It's springtime, it's storm season, right? So it's really easy to see one of the big cons of a centralized system right now. But there's different ones. So those two questions, just feed it in there, because really that's a topic for a different course. The main thing to get out of this discussion board is using chatbots. They're not going away. My feeling about them is that they're basically a typewriter. It's the newest version of typewriter. It replaces the keyboard by typing entire essays at once instead of one letter at a time. We already had autocorrect, right, that would do whole words. You start typing on your text on your phone, you don't even have to type the first letter of the next word to get it. There's already a list of suggested words, right?
And then there's grammar correct too,
Yeah.
which is probably more complex.
Things like that. So there's lots of yes, that's going to be way harder than the chatbot actually. The chatbot works entirely off weighted averages. It just does thousands of weighted averages to determine when one sentence is better than another sentence. The grammar checkers, even though they don't get the AI label, there's more intelligence in them because they have to understand what the sentence means.
I was like referring to when you were talking about autocorrect. I'm like, well, grammar correct is probably just like the upgraded, more complex version of that, because it not only has to know how they're spelled, but has to know different spellings of the same word and when they use them.
Yes. So that's actually more advanced than ChatGPT because it has to understand the sentence, which is the big do not trust chatbots. They will lie to you, and then they will print out a perfect looking citation that is entirely made up to support their lie.
The problem is because they believe what they're saying, so they make it very believable.
Yes, they only had humans to look at when they were trained. So they learned from human traits. One of the big things for ChatGPT, especially, it was trained on what a good sentence should look like from social media and plagiarism checkers. Because the text-based things on social media, if it gets lots of likes, it's probably a good sentence. Same thing with plagiarism checkers. If the same sentence gets plagiarized a lot, it's probably a really good sentence. So it's a good model to look at. But when they trained it that way, they didn't tell it that Facebook is full of bad information. And then that sentence that has been repeatedly plagiarized is actually something that shouldn't happen. So it just saw it was done a lot, and it learned to do that a lot. So you have to watch those. The specialty tools, they're it's not going away. I consider it like a keyboard. That's what I think of it as. The next step up from autocorrect, Grammarly, the grammar checkers, it just gives us a full sentence. But in a lot of ways, it's a step down from the grammar checkers because the grammar checkers have to know what the sentence means. There's a lot of things. It can write the code for us. A special tool. It's not going away. Anybody in this room, you're in the IT field, heading into the IT field, you need to know how to use it, how to optimize it. So that discussion, the requiring it isn't just to see where the address is and put the thing in. You want to try to learn what will get the best results from it, how to optimize what you're getting. Any other announcements? Oh yes, another announcement. Next week, I'm going to be in Indianapolis for a 3-day meeting. So on the 20th, I'm not going to be on campus. I'm not going to be here to run our course. All the meeting stuff will be done by then. So I was kind of considering doing a short virtual class that night and counting that as one of the attendance required days. Y'all might remember when we looked at the policy, it said traditional classroom or virtual, but not at the same time, explicitly in there. So those required days, we could fill one of them with a purely virtual day. I will not be on campus that day for sure, though. Really, the choice between doing that and canceling class for that day matter, it's just how far we get this week. Because got stuff to talk about software this week. And this is an active subject we learn by doing, so I don't want to stand up here and talk until 8:30 every day. We did that in the hardware. We were here till 8:50 every day in the hardware lectures. I think we went till after 8 last week. And we learn by doing, not by talking about it. Talking about it is the vocabulary term, the keywords. So we can learn to speak like an IT person. So we get through the software stuff, and then next up is networks. And likewise, I have, just like software, I have 3 sets of notes for the networking things. They're mostly diagrams, so it'll be a quick lecture. But if I have to cancel class one day that week, that would be a lot to shove in that one day. So that's what I was thinking, maybe still I'll do it virtually from the hotel room, but it depends on how far we get this week. If we finish up software and get started into the networking things, it feels like we'll get done by then, I might just cancel class that day or something, but expect to change. We won't be on campus, I can say that for certain at this point. Okay, so now our next topic. We looked at hardware, the physical machine itself. Then we looked at data, that internal representation, the thing we actually want the machine to do. The purpose of these things is to store and transmit data. Transmitting is next week with networks. But you might remember from that lecture about binary code is that's something humans have a lot of trouble working with. It's very simple once we see it, right? And that's the thing about machines is machines can only do simple things. So if something seems complicated, what you really need to do is take a step back to a lower level and build up to that, because the machine cannot be doing something complicated. Machines can only do something simple. So as you're studying and you see something that seems overwhelmingly complicated, you probably skipped a step somewhere along the way, because the machine has to be doing something simple. Just a keynote from things I've seen over the years when people research stuff, they'll try to make sense of something beyond the level. But if you progress in the right order and learn all those simple pieces along the way, the machine cannot do anything difficult. It's not possible for it. Ones and zeros, the machine can either do something small or it can't, or it does nothing. That's the only options we have. So anything the machine does has to be simple. I use the words complicated and complex very precisely whenever I'm giving lectures. Complex means lots of parts. Machines are great at that. They can do lots and lots and lots of parts, right? We measure things in we measure machines moving gigabits at gigahertz speed. That's the prefix that means billion. So we're moving billions of bits, billions of times a second. They can do lots and lots and lots of little things, so they're complex. They can handle complexity, but they can't handle complicated. They can't really move 2 things at once. That's why we have multiple CPU cores. If we want a machine to do 2 things at once, we actually have 2 computers in many aspects. Just the CPU is small, so we can put several of them in one box. This week we're going to talk about software. So hardware, physical device, data is what we want to get of that physical device, but it's hard for humans to work with. So software, the definition is the set of instructions data or programs used to operate computers and execute specific tasks. I should probably say that whole sentence out loud and then write it down. Used to operate computers and execute specific tasks. That's a good way to say it. The technical definition is just programs and other operating information used by a computer. So at some point, right, that technical definition that you would go read out of the dictionary is something that's probably going to show up on multiple choice quizzes. And we see those in class all the time. But when you go to get your certifications, those nice pieces of paper that hang on the wall and fill the requirements that you see in job postings, you don't get certified, like, for example, in Python, as a Python programmer. You don't get certified as a Python programmer by writing a bunch of Python code. You get certified as a Python programmer by answering a bunch of multiple choice questions about Python. So things like technical definitions do show up even outside of the classroom. But the technical definition you'd see in a dictionary is programs and other operating information. Programs and other operating information used by a computer. And there's a keyword there that kind of says a lot about what it is. We've talked about that a few times in this class, that general flow from data to information to knowledge to wisdom. The definition of software involves information, not data. So it is a step up that progression. It is useful data. It's not just any arbitrary data. It has to come in context so that we can do stuff with it. In general, I think everybody's familiar with the word software itself, right? Not really a new word in our society. We talked about how the physical device is able to store, retrieve, manipulate patterns of switches. So this example, we have an electrical circuit. Maybe our first switch is off. Our next switch is closed or turned on. Then we have one that's off and one that's on. Somebody want to tell me what that means? As far as data. So I wrote it as switches. Usually we'd write that as ones and zeros, right? So I'll use 0 for off and 1 for on, which is not a standard. We have to define that every time. These are arbitrary symbols. This is a physical switch that is either on or off. Usually we use 0 for off, 1 for on, but there's reasons why it can be beneficial to switch that up. Anybody remember what number that represents? Looked like you were going to guess for a second and shook your head. So it's just like our base 10. We have all our columns, only they're going to be powers of 2. So anything to 0 power is 1, 2, 4, 8. And then we end up with a yes or no question. So if we add up the guesses, no, we don't have an 8. Yes, we have a 4. No, we don't have any 2s. Yes, we have a 1. So we have yes on 4 and 1. Gets us back to 5. So the data, we have that physical device doing that. We represent it with symbols because drawing a circuit is kind of a mess at times. But what the machine actually does is very difficult for humans to work with. Except for a few special cases mostly only electrical engineers work with the machine language, work at that level. And the times that humans do regularly work at the machine level, for those of us that aren't electrical engineers, well, I said it's a lot to keep track of. And I mentioned when we were doing hardware, my favorite hobby on the weekend is to build things with microcontrollers and single board computers. Even if you're the electrical engineer to put this together, it's hard to keep track of. And not like if it's set on the shelf for 6 months and you haven't had time to work on it. Like if you did it 20 minutes ago, it's still difficult to come back and remember what you were doing 20 minutes ago, 20 minutes previously, if you don't have some good detailed notes. That's one thing about learning electrical engineering, is learning to keep really good notes so you can keep track of what that machine's doing. It's hard to work with. So when we normally need to do it, we actually have to make it more complicated. It's too simple. That's what makes it hard. And like adding up this number, we ask a bunch of yes or no questions and then combine those at the end. Humans don't need to break it down to that most basic level. So in general, if we're going to work with it, we work with hexadecimal. Work in hexadecimal, which is really, we're working 4 bits at a time. Humans can handle more than 2 states. So we just combine a bunch of them, take 4 at a time, and then we have 16 possible states to deal with at once instead of 2. So we really actually make it more complicated so that we can work with it. So like pixel color. We're on software this week. Next week in networking, network people do that a lot too, because the machines know about each other because of numerical addresses, which is really lots of binary code. So the network administrator might need to work with the binary code, the same language the machines know about each other in which case they type in the address in hexadecimal format instead of typing all the 1s and 0s. Forest green. So I looked this up on a particular machine, on this particular machine, by the way. The examples I'm going to put up here on the board were looked up on this laptop that's sitting up here right now. So if we use the word forest green, what this laptop activates is the hexadecimal color 228B22, which base 16 numbers. So we take them 4 at a time. We could do that columns things again. We have a 1s column and a 16s column. So that's really 2 16s plus 2 1s. So that'd be a 34 is the number we would call that. But the reason we do that isn't because that's a way to write 34. It's because that's a way to write 2 2. And if each one is spread out into 4 bits, 2 is going to be 0 0 1 0. Well, the other 2 is obviously the same. 0 0 1 0. 8 is 1 0 0 0. So 8 is 2 cubed. And remember, B is, once we pass all our digits, we need 16 of them for hex. So as you're getting used to it, I would recommend still counting on your fingers. So A is 10. So if you count up to your fingers, you get to 9, and then go back to no fingers for A, then B, C, D, E, F. We'll get all 16 of our digits. But doing that, A, B, so that's going to correspond to 11. So 11 in binary, we'd have an 8. So does 8 fit in 11? That's that yes or no question, which this is not new. Egyptian scribes did math in binary. They wrote base 10 numbers like we do, because we have 10 fingers, but then they would turn them into binary. So they had a bunch of yes or no questions, do the calculation, and turn it back to a base 10 number to write it at the end. Do we have an 8 and 11? Yes, we do. Leaves us 3. So then the 4s, do we have anything in the 4 columns? No, there's only 3 left. So no 4s, but then we need a 2 and a 1 to add up to a 3. And then 2 again on this particular color, I went and looked up. Comes back to 2, and we already have that right over here. 0, 0, 1, 0, 0, 0, 1, 0. So this is a way to type this, and then that gives us direct control over the pixels on the screen. Right? Each one of those, each pixel takes in some on or off states. There's multiple colors in there, multiple switches, and we turn some of the switches on, some of them off, and then as they mix together in that into that color. So if we need to type this machine code, we probably want to type this. And for something like controlling the pixels on the screen, we definitely want machine language control over it. We don't want to use a bunch of arbitrary words if we're immediately flipping switches for the pixels on our screen. Same thing with networking addresses. The different machines, we might want to do it directly. Type in the way the machines know about each other to avoid human typos in that abstraction level that's to make the complicated thing, or to make the very, very complex things easier to work with. In general, though, it's hard to keep track of this. We do this like when we assign a color to a particular pixel. So we're doing that once, and that color is probably going to keep showing up in the program. We don't do every step that way. If we had to write our entire program that way, all of the changes and everything, that would be a mess to look at. So a step up from machine language, we get to the first thing we can kind of work in. It's okay if I erase this side of the board. I'm going to switch to the blue marker. I'm asking for anybody have any color issues? All the colors are fine. Okay. I always like to make sure. I've heard blue is the worst. If people that can't see blue, might as well have a white marker on a whiteboard. So a step up from machine language is assembly language. Which is still a very low level language. It's close to the machine, but not as close. This side is machine dependent. Machine language is unique for each machine. Assembly language takes it up so that the way we access this particular switch right here is unique to every single motherboard. But once we put that number in that combination of that particular combination of switches, we have that combination everywhere. Just the way we access each particular one would be different. So there's some parts that are the same and some parts that are different, and assembly language takes part of that. So we have a few key commands. Combined with binary. To create, to carry out tasks. This is what we really use to tell the machine what to do. And the one I looked this up on was a 64-bit computer. But for example, this first instruction used 2 4-bit numbers. So there were 60 zeros before that. So I left the 60 zeros off on here. And kind of abbreviated what we're doing, but I did copy this from a 64-bit machine. And then after that, we had a really long number, and then 2 16-bit numbers. So even on our longest number, there's still 48 bits, 48 zeros that I'm not going to write on the notes. So it was copied from a 64-bit machine. If I wanted to add two numbers, I'm going to do this. 2 plus 3 equals. We all know what those symbols mean, right? So I'm going to write a program that does this. In assembly language, I already wrote the answer. I could do switches. So 2 we saw is off, on, off, off. And 3 is on, whoops, come down, the switch is on, then 2 switches that are off. Just to put the actual machine in here. So how exactly do we combine this pattern of switches with this pattern of switches in such a way that the machine knows we want to add those two numbers and get this pattern? I want to draw the actual pattern so you can see what the machine's doing. The pattern is spottable. You can spot the pattern there if you look carefully, but I just wanted to put it up there. Hopefully you can see that it's a bunch of pattern matching. We need to combine those in such a way we get that. But it's hard to do at the machine level. So we added in some keywords. So one we'll have an assembly language is going to be add. Now this keyword add, and well, on the machine I looked it up on, the one sitting right up here on this podium, is a 64-bit machine. So it wrote 60 zeros and then followed those up with 0, 0, 1, 0. And then another one, 0, 0, 1, 1. Result. The first thing you'll notice is that does not go in the same order we put it in. Okay. Humans almost always would say that is 2 plus 3 equals something. But addition is a binary operation. We need two numbers to add. So before we even get to the first number, we have to tell the computer we're adding so that it knows we need two numbers. Because not all of our math operations take two numbers, right? Some of them only need one number. So we have to do operation first, then our numbers, and then a command that actually says keep that result around, don't delete it. Don't delete it. We did that for a reason. We want the answer. So it's holding that result in a thing called the accumulator. So arithmetic logic unit, we feed this into register A, this into register B. It's a circuit. It's not something that it comes in afterwards. It's like flipping on a light switch. So when we plug in, think of it as plugs. We plug this in, and then we plug this lamp in, and then the room's well illuminated. So when we put those in the register, they immediately flow through the ALU into another register called the accumulator. And that last command says, don't delete what's in the accumulator. We need that. And we're going to follow that with load. 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1. Then a whole bunch of zeros before. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there was ones in the first 16 bits, and then the other 48 bits were all zeros when I copied that. So I'm not going to write 48 zeros on the board. I don't think I even have room to write 48 zeros on the board. But load here. What that's saying is take that result that we said don't delete and load it into a spotting RAM. In particular, what do we have here? We have a 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. So add all those numbers together, and then we have the bit in RAM where this is going to start. So every RAM, like somewhere on that RAM chip is bit 0, and bit 1, bit 2, bit 3. We can go to whatever those numbers add up together and store it here. So that's why I was just copied it from one time, because if we did this again, it would probably give us a different place in RAM to keep it. Then I need to do this. So jump carry. Oh, I didn't write everything I was going to do. So this does our addition. This keeps it around. This instruction says don't delete it. This one actually puts it on the RAM chip somewhere, so we have it to work with. So what I was doing here is the equivalent of writing this in code. Let's set up some places to hold stuff. Let's say X is going to be assigned the value 2 plus 3. So add 2 plus 3, keep the result around, and load it into some place we can access it. So that's what this instruction is. And then in my notes, I wrote one more. So if X is bigger than, say, 4, then I don't know, call method, we'll do something. I didn't get that far in assembly language. It gets very, very complicated after the next line. But this condition, that's something we do a lot. Anybody seen a little bit of coding, right? Yeah. Have y'all seen some coding before? We do selections a lot. So what that looks like in assembly language is jump. In this case, we're jumping based off math. So a greater than condition, greater than, we would find that by subtracting. We take whatever's stored here, subtract 4, and if the result is bigger than 0, if we have a positive result, then we know our first number was bigger. But if we take this number, subtract 4, and get a negative number, we know our second number was bigger. Very briefly, last week we mentioned 2's complement. The way we would take complements in numbers and add 1 to get to the second degree complement, and then that turns all of our math into one operation, which is an awful mess in base 10, but in binary it's really, really easy. And that allows us to do one circuit. And when we do it that way, when we subtract, if we get a positive number, we'll have an extra bit carried over to that next column. It's just like when we're adding in elementary school, we go down the column and carry a bit to the next one. If we have that other bit, we'll jump to another spot in code, which when I did this was 11001 000 111 1100 1010 is a 64-bit number, so a whole bunch of zeros. Then a space, then another 64-bit number that went. I'm gonna go .1 .1. So then it gave 2 more 64-bit numbers that were both just a 1. Still a kind of a mess to work with. But we start to see some things that we can make sense of, right? Especially in these keywords. That binary part's confusing. This one refers to actual numbers in our registers. This one refers to a bit in RAM. This one also refers to a bit in RAM, so that if that value we have is larger than the number 4 in this case, go over to this bit in RAM and pull out whatever instruction we stored there. And then these just reset the registers. That 1 at the end is actually the positive sign, or the positive negative sign, and then that feeds into a register that automatically takes 2's complement to solve the 0 problem. We talked about that the other day. So we need that positive sign. So put 0 in both registers and just throw a positive sign on it. We're going to get rid of the positive negative signs and on the next step. Is what that is, but it's a mess to work with, right? We would not, that was just to add 2 plus 3. So kind of a mess to work with. So that's where we get to high level languages where it looks like this. I use Python syntax. I guess this is kind of like Python. Python is by far one of the most popular programming languages in the world. It's usually listed as number 1 because we actually disregard what's in that number 1 spot. JavaScript is a standard, is the official international standard for websites, and there are a lot of websites. So obviously JavaScript is the number 1 used programming language just because it's the official standard. So disregarding that obvious case, Python is the one people choose to use most often. And the thing about Python is everything about it is easy to use. When it was created, it's slower. All the stuff that makes it easier for humans to use makes it slower. So in 1989, when it was created, Christmas break 1989, there's actually a kind of interesting story around it. It's been at one point he tried to modify it and change it a little, but the original story is still there. He couldn't get out of a family event. Everybody in this room's computer people, y'all probably understand. It was Christmas time, so family reunion at Christmas. He tried to get out of it, but apparently somebody he was related to also worked there and knew that he had the week off work. So he couldn't get out of the family event. So what he did is he made up a project so that he could get out of talking to his family. And by the end of the event, or by the end of the week, after he sat there in the corner and worked on his made up project for 3 days, he kind of realized he had something really, really good going. He's like, I have to create this programming language and do it as quick as possible. And it was an excuse to get out of talking to his family. And everything about it is basically set up to be easier for the human to use. That was a problem in 1989 because all of that stuff makes it slower. We lose some of the control we have over other languages because all of that becomes automated in the background. And the computer has to take time to do that. To make it easier for the human, we pass the work on to the machine. So it slows everything down. But machines got faster and faster and faster. And 2010, 2011, 2012, that era, it wasn't bad. We would still notice that a program written in Python was slower, but it would still run reasonably quick. It wasn't slower enough anymore that a human would considerably care about it until it got massive. But then something massive showed up. In 2012, there was a huge breakthrough in machine learning. The step that finally paved the way for the chatbots, like we talked about earlier tonight. There was a huge breakthrough in machine learning, and we create models, and then we let the models train themselves. The big thing about AI and this stuff is we talk about these patterns here. That's a human pattern forced on a machine. So what AI is, not really intelligent. What it is we let the machine choose its own patterns. So instead of forcing these human patterns onto the machine, we let the machine figure out what the best pattern is. That takes time. The process is basically we tell it no until it gets it right. We give it a data set that we know that we already set up with the right answers, and the machine starts taking guesses at what the answer should be. And after it gets told no billions and billions and billions of times, it's narrowed down to what the right answer has to be, is the idea. And it develops its own patterns. But it's still basically pattern matching. But in 2012, there was a big breakthrough in that. And even in our fastest language, which is another interesting point in software, our fastest high-level language, where we're working in human level, not assembly language or not machine language, there are places where a language called C++, which is really nice. That programming language gives us absolute control of the machine. It was designed to write an operating system. Well, a language C was designed to write an operating system, and it replaced a language called B. This was done in laboratory experiment type thing. So they were moving on from language B, and it was a big enough change. They decided to give it the next letter. It was going to create an operating system, so it needed lots of control over the machine. Then somebody asked a question, like, what if we don't tell it what machine it has absolute control over? The result of that is a high-level programming language that's abstract, so it's reasonably okay for a human to work with. It does take some training for anybody who's written software. We have to learn to write the code. But once you've had that training, it's fairly easy for a human to work with, and we have absolute control over any machine we run that code on. Dangerous levels of control. It will not tell us if we're about to break our machine. We can hit run and completely destroy the machine run. So over the years, it was cleaned up, and every language that is more popular than C++ was basically created using C++. Python, not directly. C++ was used to create another language that was used to create another language that was used to create another language that was eventually used to create the language ABC, and then ABC was used to create Python. So it's way down that line, but every language more popular than C++ was created using C++. So really good programmers sat down with this unrestricted control we have over the machines, and what they chose to do was to write another language that restricted some of that control. I often like to phrase it in starting off the Java class, is we don't lose any of the power we had in C++, we gain warning messages. So we can't destroy our machine without ignoring a warning message that says you're going to destroy your machine if you run this code. Whereas C++ would just let us run the code. So lots of control over the machine. Those are for future classes. We're just looking at sort of the broad approach to it this evening. And there are some categories of programming languages. Be the next thing, but probably a good time for a break, right? This seems like a good pause point. So we have our machine language, assembly language, then our high-level languages that we actually work in, and we can start categorizing those after a break. And maybe an example after a break, but probably a good time for 10 minutes, because if we don't now, we'll have to stop in the middle of a topic, right? So my laptop says 7:08, so we'll get back to this at 7:18. See y'all in just a moment.